Let's discuss the question number 30th from test 5. This is from machine design. So a bracket is given which is attached to the wall by means of 4 rivets as shown in the figure. So we have 4 rivets. Okay, and the difference or the pitch is 30 mm. And one apply and the load applied is 20 kilonewton, and the distance, it's an eccentric loading, so the distance from the line of rivets is 80 mm. So now we are supposed to find out the diameter, appropriate diameter of the rivet, knowing that the maximum shear stress in the rivet material is 140 MPa. The tau max is 140 MPa, and we are supposed to find out the diameter of the rivet. Okay, so let's find out the rivet which is mostly which is critically loaded or heavily loaded. Okay, so this kind of problems, what we do is we first identify the center, the CG of the rivet system, which is, in this case it's quite simple to identify, and it is at the center. Okay, now this load is broken into, basically this load at the G, it will be felt as a direct load as well as a moment because of this 20. So let me just draw these rivets in terms of pluses. And so at G I have the direct load which is P 20 kilonewtons, direct load or the primary load, plus the secondary loading will be basically at the G there will be a moment because of this P, which is P into E, and that is 20 into 80 or 1600 kilonewton mm. Okay, yeah, that is the loading. Okay, so now let's see, because of this primary and the secondary loading, how are the forces that are induced in the rivet. Because of this direct loading, there will be a direct shear forces on the rivets, and that is written as Fs. Okay, so because of the direct load, there is an equal amount, all the rivets share an equal shear load, and the primary shear load Fs, which is nothing but P by 4, because there are 4 rivets, so 20 by 4 is 5 kilonewton. Okay, now because of the secondary load, generally how it is analyzed is, because of the secondary load, the forces, let the forces on the rivets be F1, which is at a distance L1, on this it will be F2, and on this it will be F3, and this it will be F4, and the distances again are L3 and L4. Remember that L4 is equal to L1 and L3 is equal to L2. Okay, so now there are a couple of assumptions that are made while solving for the secondary load. One is your F1, the forces F1, F2, F3, F4 are assumed to be proportional to their distances from the center of the rivet system. So F1 by F2, F1 by L1 is equal to F2 by L2 is equal to F3 by L3 is equal to F4 by L4. So this is one assumption, and this is one assumption. And the other thing is that PE, the total moment, has to be equal to the moment, effective moment produced by F1, F2, F3, F4. So that will be F1 into L1 plus F2 into L2 plus F3 into L3 plus F4 into L4. Okay, so now what I'll do is I'll use all this in this and find out F1. Okay, so F1 into L1. Okay, F2 I can substitute as from this relation as F1 L2 by L1, so it becomes L2 square by L1 square. Similarly, F3 will become L3 whole square by L1, and F1 L3 whole square by 1, and this will become F1 L4 whole square by L1. Okay, so in this way I can individually find out each forces F1, F2, F3, F4. So now, okay, so F1 will be L1. I know L1 is, okay, so let's just write down what is L1. L1 is 45, L2 is 15. This is easily, I mean, you can see easily from the given geometry, and L4 is again 45. So L1 is 15, L2, sorry, L1 is 45, L2 is 15 square by 45, and this is also 15 square by 45 plus 45. Okay, and P we know it's 1600 kilonewton mm. Okay, so from this I can easily see that F1 is 16, and easily calculate, and this comes out to be F1 is equal to 16 kilonewton. Now F2 will be basically L2 by L1 into F1, which is 15 by 45 into 16, so it's 16 by 3 or 5.333 kilonewtons. Now F3 is also similar to F2. This can be easily seen because L3 and L2 are same, and F4 is equal to F1. This also can be easily seen because F1 is equal to L1 is equal to L4. So we know now let's put all the direct load as well as the secondary load combinedly. So direct load here it is Fs, and here it is F1, so which is 16 here, and this is 5. On this the primary load is 5, and this is 5.33, and now on this the secondary load is 5.33. the direct load will be 5 always downwards, and on this it is again 16. So this can be seen now, it can be seen that the total load will be basically the resultant of these two, and these are acting perpendicular. The primary load and the secondary load are acting perpendicular. So on this the resultant load will be 16 square plus 5 square, and here it will be 5 square plus 5.33 whole square, and this is again the same 5 square plus 5.33 whole square, and this is 16 square plus 5 square. So the critically loaded are basically 1 and 4. Okay, and the resultant load is basically 16.76 kilonewton. Okay, so because this is the rivet which is heavily loaded, so we need to design for this, and so the load we know, the total load is the total load by area is basically the shear stress that is induced, and let's write down area of cross section. It is pi by 4 d square and tau. So now my tau should be less than tau max always, otherwise it may fail. So F is, we will use the critically loaded, which is 16.76 into 10 power 3 because to convert in newtons. So I'm just finding out this, okay, into pi by 4 d square, and that has to be, this is tau, this has to be less than or equal to tau max, which is 140 MPa Newton per mm square. So this, let's put 140 only so that I get d in terms of, okay, so d has to be greater than or equal to 12.34 mm. So let's use the smallest diameter so that it saves weight or less material we need to use. So 12.34 mm, and which is approximately, let's use 12.5. Okay, so the answer is D. Thank you.